Hello there, ATS EVS 105 students. Dr. John Schrage here, and we're moving on into the second module of the course. We're going to be learning about what the observations are actually telling us about climate change. Is the climate changing? And we're going to be talking about different types of information that we have about what the climate is doing and so on. But this lecture specifically is about surface temperatures. Where do we get observations and what are they telling us? This comes particularly from a set of readings that I've given you in this module of the course. You should always go and check the the course schedule page up on the Welcome to ATS EVS 105 module at the top of the very on blue line, the very top module. If you haven't noticed the readings, though, they are in the textbook pages 16 to 20 for this lecture, and in the IPCC 5th Assessment Report in Chapter 2, read pages 161 to 163. Some of the stuff in that assessment report will be a little bit technical, but I kind of want you to have a sense of the kinds of things that they're saying in those assessment reports. Now, back in the first module of the course, we actually defined what we meant by climate and how it was a statistical representation of what the state of the atmosphere over very long periods of time was. So now that gives us the ability to be asking, what do we mean when we talk about climate change? And how has it changed now, and how is it changing now, and how has it changed in the past? And in particular, when we are going to be quantifying what we mean by climate change, I want to be focusing on temperature. I guess we could have used other meteorological variables like, I don't know, rainfall or pressure or winds or cloudiness or something, but we have chosen temperature as how we quantify climate change, like how much the temperature has changed globally over the last century or something like that. And there's a number of reasons why temperature turns out to be our best bet of a way to quantify climate change. I mean, for one thing, temperature is the quantity that is most directly related to the addition of greenhouse gases. Now, it isn't until the next module that we're going to start by learning the physics of why that would be and so on, but the addition of greenhouse gases to the atmosphere by the burning of fossil fuels and so on is primarily changing the temperature of the Earth's atmosphere and the surface of the Earth, which then the temperature can change things like how much precipitation a region receives, or maybe things like how many hurricanes happen per year or something like that. But what is most directly affected by the release of greenhouse gases into the Earth's atmosphere is the temperature of the Earth atmosphere system. So temperature is a logical way to be describing how climate is changing. We also have better observations of temperature than we have of anything else, not just in terms of their accuracy and their precision, but also how long the records are. I mean, good old Daniel Fahrenheit, invented the mercury in glass thermometer way back in the 1600s, and it is a very easy instrument to use. It's a very reliable instrument. It doesn't really have a lot of moving parts. It's easy to calibrate and so on. This is an instrument that there's a reason why we have been using it for roughly 500 years now. Now, that doesn't necessarily mean we have 500 years of temperature observations that are of the kind of quality we would want in order to study climate, but actually, especially the Victorians in like the second half of the 1800s, they were they were obsessed with measurements and climate and so on. And as they went out and colonized the remaining corners of the world that the Europeans hadn't already taken over, they were really good about setting up weather stations. Certainly by about the 1880s, the world was actually pretty well monitored in terms of temperature by observations that were being taken by, French scientists, British scientists, etc. Really, German scientists, really pretty much every tropical island, every corner of Africa, every corner of South America was being monitored by reasonably high quality temperature observations. We can even do this into the past before we had these kinds of observations. Now, we're going to get to that later in this module when we talk about the subject of paleoclimate, or climate of the past, but it turns out there are ways to infer the temperature of a location even before we had thermometers. Now, this won't be like finding the temperature on, what was the temperature like on that particular Thursday back in, 422 BC, but what was the temperature of this area in the 4th century BC? That we can do, okay? It involves things like the isotopes of oxygen that are trapped in corals and sediments on the ocean floor and stuff like that, but we'll get to that when we do paleoclimate in more detail. Now, It's actually fairly tricky to study the climate, and I'm sorry, to study climate change in particular, when we talk about temperature directly. Your book uses the word absolute temperatures. I'm not nuts about that term, but let's go with it. You know, like as in the temperature in Omaha in January 2015, the average temperature was 32.5 Fahrenheit. That actually turns out to be fairly tricky. We tend to want to use, instead of describing things in sort of the temperature, to describe them in terms of what are called anomalies. In this case, we're talking about temperature anomalies. And the temperature anomaly is the difference between the actual temperature at that time or that location or whatever, and some reference temperature. Typically, that reference temperature is some kind of average. Like, for example, if you wanted to know the temperature anomalies in Omaha in January 2015, then maybe you would have a climatology. You know, the average temperature in Omaha over the last 30 Januaries was 28 degrees Fahrenheit. In 2015, the temperature in Omaha, maybe the mean temperature was, in January was, let's just say 32 degrees Fahrenheit. So then the difference between that reference temperature, which in that case was an average, 28, and the temperature at the actual, time that we're talking about, in this case January 2015, would be, the difference would be 32 minus 28, which is 4 degrees Fahrenheit, which is whatever it is in Celsius. It is the difference between now, or whatever period is you're studying, and some reference temperature, which in most cases is like a climatological average. So like here's a map of temperature anomalies for the whole world. It happens to be June 2009. This is actually one of the figures from your textbook. It's just in the textbook it's in grayscale, whereas the author provides it to teachers in color as well. And so here's a map of temperature anomalies in Celsius. And so in order to do this, at every location on this map, they had to find a climatological mean temperature for June. I believe that in this case it said that it was based on the period, I don't know, the caption to the figure that matches this in your textbook will tell you. I think it was like June 1980 to June 2010 or something, I forget. There was some climatological average June temperature at every location on this map. Okay, so then in the next step on the production of this chart, at every location on that plot, they had to compute the average temperature in June 2009 from whatever sources of information they had. Finally, they computed the June 2009 temperature anomaly by, at every location on that map, taking the difference between the temperature in June 2009 and from that number subtracting the climatological June temperature. This plot then shows the anomalies, the difference between the June 2009 temperature and a climatological average temperature for June at every location on that plot. So when they colored it in then, places that are in red had temperatures that were above the June climatological average. June 2009 was unusually warm at the locations that are colored in red, and I'll just draw your attention to the fact that some of those locations are awfully warm. I mean, these places that are this dark red color here were more than 6 degrees Celsius, that's 10.8 degrees Fahrenheit, above normal. That is a big temperature difference. To maintain that far above normal for an entire month is a very large temperature difference. So you can see it's like Siberia and Eastern Europe and parts of Antarctica and so on. Blue places on the map are places where the temperature in June 2009 was below normal. Now, what this actual plot would look like will depend then on what you chose to use for your climatological reference temperature. If we had chosen, okay, I believe this plot was based on a fairly recent 30-year period. June 2009 was being compared to some climates that already were fairly warm. So to be warmer than that normal 30-year period is quite a lot. I mean, that was already a pretty warm period. If our climatological average that we were comparing it to had been, say, pre-industrial, before we began releasing greenhouse gases into the Earth's atmosphere in the mid-1800s, well, the temperature of the planet would have been considerably lower, and these temperature anomalies would seem even bigger. These temperature anomalies would be even greater than the temperature prior to, compared to whatever the average temperature was in, say, the early 1800s. So what the temperature anomalies look like do depend on what you chose to be the normal or the reference temperature that you're comparing them to. Why do we use these kinds of temperature anomalies as a way of quantifying climate change? Well, part of the problem has to do with the fact that this absolute temperature, the actual numbers for the temperature at each location, can actually vary quite dramatically over fairly short distances. For example, your book brings up the whole issue of urbanization. Cities are always warmer than, well, that's not true. Cities are almost always warmer than the countryside around them. If you have thermometers in downtown Omaha and you have thermometers, a few miles outside of the city, the thermometers inside of the city are almost always warmer than the thermometers outside of the city due to a phenomenon called the urban heat island. Okay, if you just made a map of temperatures, that would have set up a big temperature difference over a relatively small area. But if we looked in terms of anomalies, if the thermometer in the middle of the city is a few degrees above normal, probably so are the thermometers on the outskirts of the city. Those temperatures might be lower than inside the city, but they are higher than their normal temperature. So as a consequence, it's easier to see the big picture when you're looking at temperature anomalies than when you're just looking at the absolute temperatures that are being observed at each of the stations. Another example of that could be like a city that's in the valley versus a weather station near the top of a hill or top of a mountain or something. The station in the valley will always be warmer than the station up at the top of the hill, but when we make a map, that would be a mess. We wouldn't be able to tell, well, gosh, why is it cold here and warm here? If we talk in terms of temperature anomalies, if it's 1 degree above normal in the city, it's probably about 1 degree normal at that at the weather station at the top of the mountain nearby. So these kinds of temperature anomalies tend to be easier to work with, easier to make plots, easier to interpret than just working with the actual temperature observations, which your book calls the absolute temperatures. When we actually are talking about these climate change type statistics, we'll also often talk about the global average temperature. Here's a classic example of the kind of plots that you probably can find all over the place in your textbook and on the internet and so on, where we're just seeing like global average temperature over the land and the ocean over the last 132 years or something like that. And you can see the kinds of trends and stuff like that that probably don't surprise you. If they probably still alarm you, but they probably no longer surprise you. Why do we use a global average temperature like this? Well, it's awfully hard to think about the big picture if you're just talking about climate changes in an individual region. It's very often the case, especially like from year to year, that if one part of the world has unusually warm temperatures, it's often the case that another part of the world will have unusually cold temperatures. That's not just, the law of averages or something like that. It's where the meteorological air masses are coming from and going. Okay, air is cooling down as it's in contact with the ice sheets over the North Pole in the winter, and that air has to go someplace. Okay, so if we have an unusually warm and mild winter in the central United States, that probably just means that those cold air masses didn't come here, but maybe it was unusually cold, let's just say, in Western Europe, because maybe those cold air masses tended to end up in that part of the world instead that year. Okay, that's interesting, but that's not really what we're doing when we're studying climate change. What we really want to know is, for the whole planet, how has the temperature changed? I don't care about the fact that it's a little warmer here and a little colder there. How did the whole planet average out? We can balance that all out by computing the average for the whole planet. How we actually compute a global planet temperature is a very complicated bit of math. In fact, it's a whole discipline within math called objective analysis. And we are definitely not in a 100 levels introduction to understanding science type course going to go into the math of objective analysis, but suffice it to say it can be done. We can estimate the global temperature for the planet based on the observations that we get from weather stations and so on that you're going to be seeing in a little bit. Such a number can exist. You can see on this diagram here that we have error bars around those numbers. At any given time, there is a range of temperatures that the Earth could be. The true average temperature of the Earth is within some range, but we also have an estimate of what the average temperature of the Earth that is our best guess of what the current temperature is. In this particular case, by the way, I just want to draw your attention to the y-axis of this particular plot. Notice that these are actually the global temperature anomaly based on a period of 100 years that was the 20th century. So, I mean, they're not saying that the average temperature on the Earth is like what would be about 0.6 Celsius. They're saying that the average temperature of the Earth is about 0.6 degrees Celsius warmer than the average temperature was across the 20th century. And the 20th century, of course, was already warm compared to, say, the 19th century. All right, before we move on to a second part of this lecture, I want to ask you two questions, okay? Again, this just sort of provides a little bit of interaction in these online lectures and so on. Question one. If a temperature anomaly is positive, A, temperature has to be above 0 degrees Celsius. B, the temperature is greater than some reference temperature. C, the temperature must be increasing with respect to time. Or D, all of the above. Okay, look through these choices and then follow the links below this video based on your choice, and you'll get some feedback before we move on to question 2.